All right. Today is Friday, November the 13th. Oh, really? Is this Friday the 13th?
Yes.
Oh, wow. Oh, we got
yeah.
shut down on a Friday the 13th as well?
Yeah, March.
Oh, no, that's a very bad omen. Okay, say hi and use your Wi-Fi. Oh. All right. Are we reading my email or no? That's up. Friday the 13th. The compound urea, and you will find that in AP Chemistry, they love this compound. They use it all the time in problems. Okay, now we've never heard of it before, but that doesn't matter. We just look at the structure, and the structure is going to tell us, things about it. It's widely used in chemical fertilizers. The Clee-Lewis electron dot diagram is shown above. Identify the hybridization of the valence orbitals of the carbon atom. So this carbon right here is going to be undergoing which type of hybridization? sp2. And again, Zoe, how can you just know that real quickly?
AX3.
Because it's AX3, right? And again, just from the mechanics part of it, we have 3 sigma bonds and 1 pi bond. What's the only type of orbital that can form a pi bond? P orbital. So we had to have one of the P orbitals left unchanged in the carbon to overlap with the oxygen's P orbital side to side to get that pi bond. AX3 is the easiest way. Got to add up to 3, so sp2 adds up to 3. All right, so that's easy. No explanation needed. You just list. That's a 1-point question. Urea has a high solubility in water, due in part to its ability to form hydrogen bonds. The urea molecule and 4 water molecules are represented in the box below. Draw one. You'd be amazed when you grade these how many people draw like 6. Okay? The directions say draw 1 dash line. So draw 1. Okay? Don't draw more than 1. Draw 1 to indicate a possible location of a hydrogen bond. And in a hydrogen bond, what's going to bond to what? Okay? So we have a carbon, nitrogen, hydrogen, hydrogen, oxygen, nitrogen, hydrogen, hydrogen, right? And then this is my oxygen, hydrogen, hydrogen. So where is there going to be a hydrogen bond? To this oxygen. Notice here that the hydrogen gets trapped between 2 highly electronegative elements. Now, that's just one possibility. That's all you have to do. But what are other choices that you could do? Right there is another one you could have drawn. So then this bottom one right here is another one that would have been a good one. This one, really the hydrogens would come in contact and it wouldn't be a good choice. There's nothing really coming to this oxygen here. So there's not a good choice. Plus, you don't really have a hydrogen on this one. Okay, so you could have had any one of these 3, but only one of them. Okay? But any one of the 3 would have been correct. Are we all good with being able to recognize and identify hydrogen bonds? What are the only 3 elements that form hydrogen bonds? Both, fluorine, oxygen, nitrogen, right? And what has to be true about those? What has to be attached directly to them? Hydrogen bond. Hydrogen. Okay. A hydrogen has to be attached directly to, on both of them. Then the hydrogen gets trapped between the 2 highly electronegative elements. So again, remember, this electron is being pulled strongly this way, so this is going to be a very strong positive charge because the nucleus, it's only got 1 electron, it gets pulled away. So now we just have that proton, very strong positive. And then this is a highly electronegative oxygen, so this is very negative. So it draws. Now, do not put the charges when you're drawing this. Just draw the dotted line. And if you have to draw the molecules, just orient them this way. Don't put the charge on water. Water is not charged, it's neutral. It's polar, but if you put the charges on there, they mark it wrong. You really had to do that on the last test, too. I made you draw it and draw in the hydrogen bonds on that. Okay? The dissolution of urea, what is that a fancy way of saying? The dissolving. Okay, so they use the word dissolution all the time, it just really means dissolve. Okay? A student determined that 5.39 grams of urea with a molar mass of 60.06 can dissolve to make 5 liters of saturated solution. Alright? How do we calculate molarity? Moles per liter. How do we change grams to moles? Molar mass. Okay, so everybody tell me what to do. 5.39 grams, yeah.
Over 5 milliliters.
Oh, you're going to do it that way, okay. 5.39 grams over 5, is it 0.00?
Times 1 mole over 60.06 grams.
Okay, that's going to give me moles per milliliter times,
Times 1,000 milliliters.
and that's going to give me moles per liter, which is molar mass, which is molarity. Okay? Yeah, I think you can see that. So this turns out to equal
17.9.
okay, did anybody else do it a different way? Convert it to moles first. I mean, I could have done it this way. Molarity is moles, so you can go 5.39 grams divided by 60.06 grams per mole. So what is that doing right there? Okay. What does this give me? Moles. Divided by liters, but I know that 5 milliliters is how many liters? And these are significant zeros, so we need to include them here, liters. So then it's just going to be this divided by this divided by this, okay? Which gets you the exact same thing as what you have here. Okay? So either way, this is just the dimensional analysis way, starting with what's given. This is just using the formula of molarity. The student also determines the concentration of urea in a saturated solution at 25 degrees is 19.8. So what's different about this? What changed? The temperature. Did it go up or down? It went up. So you increase the temperature, and what happened to your concentration? It went up. So what does this make it? An endo or an exothermic reaction? Endo, because of Le Chatelier's principle, as you add heat on the left, that's going to push the reaction to the right to make more dissolve. You increase the solubility by adding heat. That's an endothermic. Okay? So according to Le Chatelier's principle, adding heat as on the left side as a reactant, or you can even say, according to Le Chatelier's principle, a reaction always favors the endothermic direction. In this case, it's from reactants to products, since the concentration is increasing. There's any way you can, I mean, there's a bazillion ways to say that. Are we clear on this? Endo and exo tends to be a confusing thing.
Wait, can you say that again?
According to Le Chatelier's principle, adding heat causes the reaction to shift more towards products, which is an indication it's an endothermic reaction, because the concentration increased. Now, let's just say that you did part C wrong, and you got 22 molar. Well, what would your answer be? Exothermic. And you get credit if you put exothermic here. You won't get credit for this one, but you get credit for this answer if you answered it correctly based upon your answer in C. All right, this should be an easy money question. But so many students this year missed this, and it just drove me nuts. How many bonds does carbon form? 4. So again, when we do this is C2H5OH. C2H5OH. How many electrons do we have total? 4 times 2 is 8. 5, 6, and 1. 13, 19, 20 electrons. Okay? So, remember then we had the skeleton. They already did the skeleton. Just fill in everything with single bonds. And then we go 2, 4, 6, 8, 10, 12, 14, 16. Where do I need to go? 18, 20. Does everything have 8 now? Yeah, it's a super easy Lewis dot structure. Ethanol. Okay? Just count your electrons, do the single bonds, and then just put it around. You know, carbon already has its 4. You know, everything's got its 8. Don't make that one hard. What is the approximate value of the COH bond in this one? Okay, so COH. What's the bond angle? First off, what's the AX formula? Okay, now that has nothing to do with the answer, but it helps us get there. What's the shape going to be? Bent. How many electron pair domains are there? Electron pair domains? No, there's a bonding. There's 4 electron pairs. 1, 2, 3, 4. So what's the base shape of the electron? How are the electrons arranged? Tetrahedral. What's the bond angle in a tetrahedron? 109.5. But we have 2 lone pairs. So what's my approximate bond angle? Approximately 105. That year, AP took 100 to 110. I can't believe that they took 110. I guess 109.5 rounds up to 110, and so they went all the way down 100 to 110. Okay? But 105 is a better answer. I'm not going to be that generous.
So you covered it, yes.
Okay? All right. But we have to know bond angles, we've got to know shapes. So I guess the question you're going to ask me, do we get the molecular geometry cheat sheet on the test?
I have 3
Yes.
tests on Monday. I have 3 tests on Monday. I think we should. It's so nice.
No, you're Reagan, show.
Reagan,
I want to see what.
you can think about it, that's not a
Reagan,
problem.
I'm not
We'll have you back.
Okay, well now that's just, if that really is the case. Monday is not my day to give a test. I'll move it to Tuesday. Just because, I mean, I'm not supposed to give a test on even days, I'm only supposed to give one on odd day. To avoid you having 3 tests on the day. And sometimes you guys just gotta let me know that kind of stuff, and so I don't want to overload you. And
So do we get the sheet?
Yeah, all right, you know, give you an inch, you want a mile, right?
All right, Amar, you sold them.
Okay, well, I was planning to give you the sheet just because I'm gonna make you memorize it in May. But if I make you memorize it now, you're just gonna forget it by May and have to memorize it again. So test will be Tuesday with the sheet, okay? But it won't be open book, open note, don't even ask.
That's not all I'm gonna ask.
Okay, Quinn, what do you
Did
got?
Reagan not get one because he didn't want one?
Sure.
So,
He doesn't have to use it, he can turn it over. Okay? All right. So, Tuesday test. Those of you at home, test on Tuesday, not Monday. Monday, Princeton review. Okay, bring your Princeton reviews. Everybody bring your hopefully everybody's gotten one by now.
2020.
Okay?
2020.
2021 preferably. You know?
We blind that
Alright. During this dehydration experiment, C2H4 and unreacted C2H5OH passed through the tube into the water. The C2H4 was quantitatively collected as a gas over here. What does quantitatively collected mean? It measured, they were measuring exactly how much they collected. A quantitative, a number. But the unreacted ethanol was not collected. Why did the ethanol not come up into here? They're both, you have the ethene and the ethanol both coming through here into the water, but only the ethene is going up into the gas collecting tube. Okay, Zoe, why?
It's soluble in water.
The C2H5 OH is soluble in water. Why?
Hydrogen bonds.
Because it has the ability to form hydrogen bonds, strong solute to solvent attraction. As a result, it dissolves in the water rather than bubbling through. Okay? The ethanol is soluble due to the strong hydrogen bonds between the ethanol and the water, causing it to be very soluble, thus it doesn't bubble through. So you need to mention that it's soluble, you need to mention the hydrogen bonds. That's why it doesn't, making it very soluble.
Can you just say why the other one doesn't, or just why?
That's probably a good point, because, on the other hand, ethane is a non-polar molecule that only has weak induced dipole attractions with the water, making it not soluble, thus it bubbles through, just the kind of exact opposite. That's a good point. Whenever they give you two things, you probably need to discuss both. All right. And then lastly, some binary compounds. What's a binary compound? Stay with me, Corn. Come on, focus. Some binary compounds that form between fluorine and various nonmetals are listed in the table above. A student examines the data in the table and poses the following hypothesis. The number of fluorine atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons in the nonmetal. Based on the student's hypothesis, what should be the formula of the compound that forms between chlorine and fluorine? What would be the formula? CLF, right? Okay, because it's going to be the number of fluorine atoms is 8 minus the number of valence electrons. So how many valence electrons does chlorine have? 7. So 8 minus 7 is equal to 1. Now, why would it be CLF and not FCO? F is more electronegative. The less electronegative, the positive thing always goes first. The more electronegative thing goes last. Now, I don't know if they would have marked it wrong or not if you said that, but it's CLF. Now, you can always look here too, C, well, they didn't do chlorine at all. But the F is always going last in all of these because it's the more electronegative element. It's the most electronegative element. In an attempt to verify the hypothesis, the student researches the fluoride compounds of the other halogens and finds the formula CLF3. Now, this is a deal with the new AP test. It's very wordy, okay? But you just got to read through the fluff and just get to the important stuff. So it says, it finds the formula CLF3. So this whole question is, draw the Lewis structure for CLF3. Okay? All this other junk is just superfluous, distracting information. Draw the Lewis structure. Well, chlorine has 7, Fluorine has 7, so it's 7 times 4, 28 electrons. Fluorine, 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 fluorine. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where do the extra electrons go? 26, 28. There's your Lewis structure. Now, the next question says, 2 possible geometric shapes for the CLF3 are trigonoplanar and T-shaped. The student does some research and learns that the molecule has a dipole moment. What does that mean? A molecule has a dipole moment. It's polar. What does that mean about its shape? It's asymmetrical, not symmetrical. Okay? So, where are we? And so, which of the 2 shapes is consistent with the fact that CLF3 molecule has a dipole moment? The T-shaped, okay? Because if it was it the other one was trigonoplanar?
Yes.
Trigonoplanar is going to be what AX formula? AX3. Whereas this one is AX3E2. What's this shape going to be? Oh, there it tells you, T-shape. Okay? So how do we put this into words though? Go ahead, Em.
I said, because the molecule is polar, it has an uneven sharing of electrons. The best way to represent this would be through an asymmetrical T-shape that causes an uneven sharing.
Okay? What are the key things that she said to make her answer very correct?
Uneven sharing.
You gotta say it louder.
Uneven sharing.
An uneven sharing of electrons due to an asymmetrical shape, then they tell you the T-shape, it's a T-shape. Okay? Whereas, I mean, if you wanted to, you could say if it were trigonoplanar, it would be symmetrical and nonpolar. If it were. Okay? I don't know if you would have to say that on this, if you just can say the asymmetrical T-shape causes an uneven distribution of electrons, so it's polar. Whereas the trigonoplanar would be symmetrical and nonpolar. We're all good with being able to identify polar, nonpolar, explain uneven distribution of electrons, even distribution of electrons, asymmetrical, symmetrical shapes. We're all good there? See, you guys are really ready for the test, hardly without even studying, but you're lucky I'm so benevolent. All right, in an attempt to resolve the existence of the CLF3 molecule with the hypothesis stated above, the student researches the compounds that form between halogens and fluorine and assembles the following list. Based on the concepts of atomic structure and periodicity, propose a modification to the student's previous hypothesis to account for the compounds that form between halogens and fluorines. What did we say existed on this one? CLF, CLF and CLF3. What's the trend? Okay? As the atoms get bigger, the atomic number increases as you go down in the family. Okay? The halogen can accommodate more fluorines, and you get one more fluorine in each bigger atom. Okay? I forgot, I skipped over one. Okay, so back to 4. This is an important one. The table above gives the molecular structure and boiling points for the compound CS2, carbon disulfide, and COS, which would be, I don't know what it is. It'd be some unique name. It wouldn't be like a normal traditional name. Okay, doesn't matter. In terms of the types and relative strengths of all intermolecular forces in each compound, explain why the boiling point of CS2 is higher than COS. Now, what type of compound is CS2? It's nonpolar, right? Why? Symmetrical. It's a carbon, double bonded to sulfur, double bonded to sulfur, okay? Symmetrical molecule, so it's nonpolar. So what's the only type of attractive forces? In terms of the types and relative strengths, what's the only type of IMF? LDFs. Okay, so this is the thought process that you're going through in your brain. You have to figure that out. Now what about COS? Now this one's going to be polar because here's your oxygen, carbon, sulfur. Okay, looks pretty much the same, but why is it polar? It's asymmetrical, and we have the polar bond, so the electrons are going to get pulled this way. It's asymmetrical. Remember, there's only one S. Okay, making it polar. So what type of attractive forces are between it? Dipole-dipole and LDS. So if I didn't have this information right here, my instinct is going to say this one's going to have the higher boiling point than this one. Because it's got the dipole-dipole. But what's the data tell us? You got to go by the data. So what does that mean, the fact that this one is 319 and this one is 223? These LDFs are stronger than the combined dipole-dipole LDFs of the COS. Why will that be? Because sulfur is larger than the oxygens, you have more electrons in CS2. The electron cloud is larger, making it more polarizable, increasing the strength of the LDFs, causing it to have a higher boiling point. Always look, what type of substance is it? The previous questions dealt with ionic ones. These are all this packet was all covalent ones dealing with IMFs. What type of compound is it? What type of IMFs are there? And then when you have the data, this always is the determining thing. That for sure tells us these attractive forces are stronger than that one. Okay? Is there anything that's fuzzy?
What did we do here?
What?
What did we do at the beginning of this unit?
We did ionic bonding and metallic bonding. So we need to know why ionic compounds are brittle. Why is this brittle? Why when I hit it does it shatter into pieces?
Because it shifted.
What shifts? What happens when you shift it?
That ion shifts and they repel each other or something.
They repel. Why? Because what gets next to what?
The negative.
Positive gets next to positive, negative gets next to negative, and they repel instead of attracting. So we have Coulombic repulsions rather than Coulombic attractions. Okay? Do they conduct as a solid? No. Why? Okay, the ions are in a rigid crystal lattice structure that they cannot flow. How do we make them able to flow? Melt them or put them into water. Okay, have them dissociate. Okay, why do metals conduct electricity?
sea of electrons.
The sea of free-floating valence electrons. Okay, why are they malleable and ductile?
Because like they don't, yeah.
The sea of free-floating valence electrons, basically. But when you change the structure, the electrons can move and keep positive and get next to positive. Okay? What are our 5 covalent network substances?
Graphite, diamond,
Graphite, diamonds,
silicon,
silicons,
sand,
sand, which is,
SF,
I heard it,
S,
SiO2, and then that sick molecule, silicon carbide, SiC. Okay? So what's unique to covalent network? Do they form molecules? Just these huge crystals, but what's different between salt and a diamond is here you have ions, positive surrounded by negative surrounded by positive in a crystal lattice structure, whereas in a diamond you have carbon atom covalently bonded to carbon atom, covalently bonded to carbon atom in a 3-dimensional crystal lattice structure. Okay? And based on the cost of the engagement ring that I just bought, okay, there's a big difference between a covalent network and an ionic crystal.
You should have gotten her a graphite ring.
Yeah. Hey.
That would've gone over.
Do we have to know like the reasons behind hybridization?
No. The only thing you have to do on hybridization is what we've done on all these problems, is just what's the hybridization on this atom? Super easy. Again, I just couldn't go through and just tell you to memorize that without giving you some kind of foundation of what it was and why we do it. So that is really just hopefully making it make more sense, but the application is just SP, SP2, SP3, just labeling. You do have to know how to do formal charge. Okay? But that's a small thing. I mean, in one question. I've only seen formal charge questions on, you know, like 1 out of every 3 years, probably due for one. We need to just be familiar with it, you know. But you do need to know formal charge. Do we need to do a practice one on formal charge? All right, that's close enough to 5 minutes. I don't know if that was 5 minutes or if that's 4 minutes. Okay, so let's look at this. So the first thing I'm going to do is I'm going to draw just a normal Lewis dot structure. Okay? Which is, by the way, what you do unless it specifically says formal charge. If it doesn't mention formal charge, don't try to do it in terms of formal charge. Okay? Just do it where the octet rule is all satisfied. But I have 5 electrons. I have 6 electrons. I have 21 electrons. Okay, so that's 27, 32 electrons. So I'm going to say phosphorus, oxygen, chlorine, chlorine, chlorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. It appears like that's a great Lewis structure. Okay? But now let's see if we can minimize formal charge. So the phosphorus. The phosphorus is going to be 5 minus 1/2 of what? 8, right? Minus 0 is going to equal 1. The 3 chlorines, you have 3 of them, they're all the same. It's going to be 7 minus 1/2 of how many? Just 2. Minus 6, but that's going to end up equaling 0. The oxygen is going to be 6 minus 1/2 of 2 minus 6, which is going to equal minus 1. Okay? So we're all good with that, so what do we need to do? you take from the negative and share with the positive. So I need to form a double bond between the phosphorus and the oxygen, because now the phosphorus is 5 minus 1/2 of 10 minus 0 is 0, and the oxygen is 6 minus 1/2 of 4 minus 4, which is equal to 0. We minimize formal charge. Okay? Any other questions? That was a good one. What I have next for you is just 10 or 11 multiple choice, practice multiple choice questions. All right? I'll make a note again for Princeton review tomorrow, Monday. Tomorrow, remember the next time we meet.
So for formal charge, you're trying to get them all to 0 because like before it was like -1 and positive.
If it's an ion, yeah, but if it was positive one, negative one, you want to get every element as close to 0 as possible.
Okay. I just thought it was 0 for the whole thing.
No, the whole thing always is gonna add up to 0. Now, if it's an ion, it's gonna add up to the charge on the ion.
Okay. That makes sense.
This, not on a piece of scratch paper.
No.
Why?
Is this for ours? Us to
Yes, that's yours. Again, no love lost for trees. So you can answer right out to the side and do scratch work on the side.